As storm chasers head out on the open roads this severe weather season, a UW-Madison atmospheric scientist is staying put, tweaking his computer modeling to find out if he can predict the world's most devastating weather events known as supercells. Michael Schlesinger sits down with Dr. Leigh Orf to find out what he's working on and how his findings can benefit all of us.
Why do two supercells on radar but look very similar in very similar environments? One produces a long track EF5 tornado and one produces maybe an EF0 that lasts for 2 seconds or doesn't even produce a tornado at all.
A question Dr. Leigh Orf and so many of his contemporaries in the field of meteorology ask themselves every chance they can. Why do some dynamic thunderstorms produce tornadoes and others don't? This UW-Madison scientist working for the Space Science and Engineering Center is doing his part to find the answer through intricate weather data and computer modeling.
I take another model, I create a lot of data, and then I do analysis. It doesn't require the supercomputer anymore, but can be done on a smaller machine, and then I have years and years to analyze that data.
A graduate student is also helping with research. One big finding could be the key to unlocking the mystery behind tornado development. It deals with spinning air near the ground being lifted into a storm, basically feeding on itself.
We've discovered a feature we call the streamwise vorticity current that we're in the process of showing that this feature helps to make the updraft stronger near the ground. When you have a very strong updraft near the ground, so you have rising air coming up from the ground, almost right above the ground, that's theoretically that should help to sustain and initiate tornadoes.
A driving motive behind what Dr. Orf does is to pinpoint the precision of where a tornado will strike while reducing the false alarm rates of warnings actually issued. Of course, with an ample amount of time to warn people as well. A new federal initiative wants an hour's notice, in fact.
Very targeted warnings for very targeted tornadoes. We're not there yet, so my work is really just about understanding the inner workings of supercells. That work will eventually filter out, I hope, will eventually filter up into the operational world where it can be used to help make better forecasts and then hopefully save lives.
The Doppler radar is such an important tool when it comes to analyzing that perfect storm.
We can see winds as well, we can see what's called radial velocities, whether the wind's coming towards you or away from you. But what we'd really like to be able to do is look at a radar, a plan view of a supercell or a radar scan and analyze that and say, wow, this storm really does have precipitation patterns or precipitation habits or whatnot that are highly indicative or linked to real tornadoes forming, or maybe, hey, this one looks really good, but it doesn't have that signature we're used to seeing. So we're trying really hard to use radar to give better forecasts and trying to squeeze all the data we possibly can out of weather radar.
And while Dr. Orf does his work, he acknowledges he's more of a virtual storm chaser and not a real one, literally, on the front lines.
I just don't like getting close to them. There's plenty of people who are good at that and who like to do that. I'm good at computers, and I'm happy to sit in my office or my downstairs office and work on the supercomputers and try to chip away at that aspect of the problem.
How do you know when you're done?
You're never done in science. I mean, in my lifetime, I hope to achieve running simulations like my initial simulation that I did multiple times, on a desktop computer, and then being able to do that before the storm forms, feed that data into the operational world where they can give very accurate forecasts.
Looking ahead as the impacts of global climate change loom larger, there are other concerns beside destructive tornadic activity to worry about, according to the experts. There's also drought, flooding, and rising sea levels to keep watching, all in a day's work, or maybe a little longer, like at least a few generations.
I have a huge respect for Mother Nature, and more recently, a lot of respect for the complexity of physics and fluid dynamics that sort of underlies these storms. There's things that you see when you run these models at high resolution that should mimic what's happening in the real atmosphere, that if you don't run at high resolution, you completely miss, and you might get an idea about a storm that's not quite accurate. So as I pursue this work, I become more and more fascinated by Mother Nature, and it opens up even more questions that'll keep me busy for a long time.